thanks for joining, everyone. As a reminder, what we hoped people would do before starting the tutorial was have a look through the slides themselves and a look through the IIT 3.0 paper by Oyutsumi. We will be running through the slides in depth in this tutorial, and if we have time at the end of the tutorial, we'll also be doing some question and answering about the Oyutsumi 3.0 paper. So the tutorial is being recorded currently. The break time and after the tutorial, the question and answers won't be recorded, but the tutorial itself will be recorded. If you have a question during the tutorial, please type it into the chat box. My chat has gone missing because I'm sharing screen, but the rest of you should have access to it. And whoever is hosting at the time, so either me or now or Angus or Yota, will either pick up on it at the point you write it in, and then either they'll just address the question directly, or we'll ask you to speak the question out to the presenter. Or we might defer the question for later if the answer to the question is obvious and it's going to come up in a slide or two. If you want us to remove your question from the video recording, please also say that in the chat box. Once we're finished, the tutorial will be made available on YouTube for anyone in the future. So the learning objectives will be the very first part of the tutorial. We're briefly going to talk about the IIT axioms and a historical overview of IIT. That's going to be done by Angus. Then the bulk of the tutorial will be on understanding the computations behind PyPhi, which is the Python software used to actually do IIT calculations. In section 3, which is going to be scattered, learning objective 3 will be scattered throughout the tutorial, but we're going to be having a brief look at how we apply IIT to actual neural recordings. And then at the end, in the question and answer section, if we have time, we'll be looking at some of the limits, scopes, and approximations of IIT measures. So specifically, we're going to have that overview. We're going to have the first section, then a little break, then another section and a little break, then the final section, and then the wrap up and the Q&A. If anyone has any questions before we get started, they can ask them now, but otherwise I'm going to hand over to Angus.
Okay. All right, so I'm just going to go through briefly the kind of core ideas behind IIT before we get into the detail of the actual calculations. And hopefully you can kind of see how these core ideas give rise to the calculations later on in the actual main slides. So the basic problem which IIT is trying to tackle is explaining consciousness from physical interactions. And just historically, the previous approaches in linking physical interaction to conscious experiences is kind of finding correlates. So if someone reports seeing redness, then we just try to correlate to some sort of neural activity. But as we all know, we can't really explain much using just correlates. So we need some sort of grounded theory to explain how consciousness can arise from physical interactions. Integrated information theory comes up with 5 key axioms or core principles, and basically every calculation in IIT is based upon these or derived from these. I'm just going to quickly go through them quickly before we go into the tutorial slides. So the first of these is information, and you can kind of think of it as sort of a conscious experience has to exist to a system. So in a sense, you have a system which is interpreting something, and the sort of thing which it is interpreting is information. So you have, if you think of information in the classical sense, you have some sort of sender and receiver. So the sender might be a book and the receiver might be someone reading the book. And through light rays from the book to the reader, you get some sort of information. This is the kind of the main idea behind it. And of course, with information, you have some sort of delay before information can be sent or interpreted by the receiver. The second core idea is intrinsic existence, and this is the idea that each experience is intrinsic to a system. So I can have an experience and you can observe everything about me, but you won't necessarily have the experience that I'm having directly. And so what this means is, if you consider information, the book and the reader, essentially what's going on is the book and the reader are the same thing. So the sender and receiver are one system. And basically the idea is the state of the system is being read by the system itself in order for a conscious experience to occur. The next is integration, and this is the idea that each experience is whole and unified and can't be split into two separate experiences. So if we consider the system, the question is kind of, the system consists of some set of physical components, and the system consists of some set of physical components. And the question is kind of, do these components exist as one whole system which is reading itself, or is it two separate systems, one which is a sender and one which is a receiver? And how we look at it is kind of, if you unfold the system through time, so on the left is, say, time one, and then on the right is in the future, then what we want to look at is everything interconnected and affecting its other nodes in the system, or do you have a case where you have a subset, say like A and B are affecting each other, but C is not affecting A, B? And this would be a case where there's no integration between all the parts of the system. The next core idea is composition, and this is the idea of how things compose together to form a higher level experience. So for example, you might have an experience of blue, and you might have an experience of a book, and in order to have an experience of a blue book, the concepts of blue and book have to compose together in order to form this higher order blue book experience. And so how the high level way we want to assess this is kind of, you have our system, and we want to look at how each part of the system affects the system, so A, B, and C, and then also when we compose A, B, AC, and then BC, how these affect the system above and beyond the independent parts, and then also how ABC, the whole thing, affects the system. And finally, the last core idea is exclusion, and this is the idea that your experience is definite and it's not kind of a superposition of multiple experiences which lead to some sort of blurry experience. So your experience is what it is. It isn't what it is plus a subset of what it is, and it isn't what it is plus a superset of what it is. So this image here is kind of, your experience, but your experience is not your experience plus, say, just a black and white version of the experience. And how this translates to physical interaction is kind of, if we consider, say, a cause and effect in the system, is it just one single cause which is causing effect, or is it a multiple time points causing effect? And the idea of exclusion is we have to find the specific temporal scale and also the spatial scale which generates consciousness, and that is the only scale which is relevant for consciousness. So hopefully these ideas will kind of, you'll see them come out throughout the actual Pi-Phi tutorial slides, but those are there, and that's what they're based on essentially. And so now I guess I'll hand over to Yota, who's going to start the actual Pi-Phi slides.
Before that, maybe I'll just make some comments. So as you might have already noticed, that the IIT is quite distinct or very different from any other types of the information theory or mathematical tools or neural correlates type theories of consciousness, like global workspace theory or any other things. First of all, it starts from the characterization of the phenomenology or conscious experience, which is true according to Tononi and colleagues for any consciousness, and that's the identified 5 properties or axioms: intrinsic existence, information, integration, composition, and exclusion. And the idea is that from these 5 principles, we really want to derive all the mathematical structures. Okay? And that's what we are going to explain in the second part. And as you will see, there is always any kind of, there is always remaining ambiguity about what to consider mechanism or what to consider as cut and things like that. But eventually, when the IIT theory becomes complete, it should be all derivable from the axioms. That's the sort of the ideal goal of the IIT program. And that with that, if you have any other further questions on this sort of the most philosophy heavy component, then let's go with Yota.
Hi, can you see my slides?
Yep.
Okay, so from here I will explain how we can compute phi, integrating information from a physical system. I will explain the first two sections, and Ariel will explain cause-effect repertoire integrated mechanisms. And then finally, Angus will take over it and explain the last three sections. So first, in this section, I will explain what kind of physical system IIT assumes and how we can compute TPM as a representation of the physical system. So the theory assumes that the physical system is a network of elements as shown in this figure. And elements can be in one discrete state at a time. So let's say in this slides, we think of binary states. So element can be in on or off state. And each element receives input and provide output. And the state of element is determined by the input and its input-output function. And the input-output function is characterized by transition probability matrix, TPM, that describes the probability of state transition. And this TPM is computed by perturbing the system into all possible configuration, which means just try all possible states and then record the results. I will explain how we can compute TPM with a single element example. Say, in this case, let's focus on element C and receiving two input from A and B. So what we need to do is first perturb the system or element in this case, and then record the results. So first, let's input off states from both A and B at time step t, and then record the results. So on the left side, what we will see is that the probability distribution. So when given this input off state from both A and B, the C will be off states with a probability of 1 and will be on state with a probability of 0, which means that when C receives off states from both A and B, C will always be off states and will never be on states. This is what this matrix means. We can just try the same things for all other possible input. Let's say in this case, input on from A and off from B, and then record the results and get the probability. And then again, repeat the same thing for this and get this, and then get this. Try this and get the result for this. This is TPM for element C. And as you can see, in fact, in this case, C can be considered as an AND gate because the state of C can be on only when C received on input from both A and B, and otherwise C will be off. So in the previous example, C has an input-output function which is deterministic, but generally speaking, this input-output function can be non-deterministic. So for example, in this case, C can be off when given off states from both A and B with a probability of 0.9, which is not deterministic. So maybe C can be considered as a noisy AND gate. Yeah. So in the last slide, I explain how we can compute TPM for a single element, but we can do the same thing for a larger network. So in this case, we have element A, B, C, D, and consider this as a whole network, and then compute the TPM representing this whole network. Again, to get TPM, what we need to do is basically the same, which is perturb the system first and then record the results. For example, we can just try these states at time step t, and then record the results at the next time step t plus 1. And in this example, we know the structure of network, which means that, let's say, element C received input from both A and C, but not from D. But generally speaking, when applying or computing TPM from neural data, we don't know this underlying structure because we don't know which, let's say, neuron connected to the other or something like that. But basically, in order to get TPM, what we need to do is the same. So first, perturb the system, and then observe the results. That's what we need to get TPM. So in this larger system, we will get this TPM as the representation of this system. So the difference between this network TPM and the previous element TPM is that in this case, the network has 4 elements. So the TPM has, these states can have 16 possible states for current and next time step. And again, this is a deterministic network. So when given a particular input, the next time state will be determined only by it without uncertainty. So in the first section, I explained what kind of physical system IIT assumes and how we can compute TPM as a representation of the system. In the next section, I will explain how we can focus on a part of a system and how we can compute or get TPM corresponding to the part out of the network.
By the way, before going further, is there any questions so far? Either in the chat or director speaking? If not, okay, let's move on. Somebody wanted to say something?
Yeah, I was just going to check, Yota, did you want to switch to the slide showing the building a TPM from neural data now or after the end of your session?
Maybe now is good. Yeah.
So that's the theory for IIT, but that's very abstract. These discrete elements with discrete states. So Yota's given an example of how we can apply this very abstract idea to an actual electrophysiological system to try and put things in context for the rest of the slides we're going to be discussing. So he's just pulling that up now.
Okay, can you see my screen?
Yeah.
Okay, so when we want to apply the integrated information, what we need to do for the neural data is just first binarize or discretize the data, and then based on this discretized data, we need to compute TPM. So in this case, we are considering two channels shown as a red line, and from there, we can binarize that data. So here we use, let's say, median as a threshold. So if the value is greater than median, then we assign one or on states, and the otherwise we assign off states. Based on this binarized data, we can compute TPM. And that's how we need to do to apply IIT to neural data. Okay.
Just to add, that level of the computation is something that we can do for fMRI data or EEG data and so on, if you're interested. And also, we are not saying that discretization by the median split is the only one way to do it. We'll discuss it in the end. Okay.
Okay. So in the next section, I will explain how we can focus on a part of a network and how we can get the TPM corresponding to the part. So why we need this? Because IIT says that the most integrated part of a network or system can contribute to consciousness. So in order to find the most integrated part, we just need to focus on all possible subset of a network and then assess the network in terms of integration. So here, let's say we focus on a subset ABC and call it as a candidate system. So here, basically, what we want to do is that capture the causal connection only within this candidate system and ignore the external system, external elements. In this case, D is an external element. So we want to ignore this. And the IIT suggests us how to compute the integration when given a particular state. So if we want to get the TPM corresponding to the part of a system, what we need to do is just fix the external element and then perturb the the candidate system. And these fixed external elements are called background conditions for this candidate system. And then calculating TPM of the candidate system given the background condition is called conditioning. So here is full network TPM from this full network. And here we fix these states off at the current time step, which corresponding to the above part of the TPM highlighted by red line. So first we focus just only this part and ignore the less part. And here the less part means the bottom part, which corresponding to the case when the state is on at the current state. So this is out of our interest for now. So we can just ignore the less states and then simply take the corresponding part, the highlighted TPM part, By doing it, we focus on a case when this state is off at current time step. However, if you look at the next time state, there are still these elements. So we want to ignore these states at the future time step. We can do it by marginalization. Briefly, marginalization is by taking the sum of probabilities of states that differ only by these states. So I will explain how we can do it with TPM. So first, what we need to do is that find states that only that differ only by the element D. So let's see the two states highlighted by blue line. So these states are the same if we ignore these states. So we consider the two states as the same. And what we need to do is just take sum of probability between these two columns. And yeah, the result is this. And then we can repeat the same thing for other states. I mean, in this case, the A states is on and the B states and C states off. And again, these two states that only differed by D. So we can combine these two by taking sum of these two probabilities. And then we repeat the same thing for other states. And finally, we get this TPM.
Let's complete this slide and then take the question at that point.
Okay. So by doing this, we can ignore these elements. I mean, in this case, we fix these states off in the current time step, and then ignore these state in the next time step. Okay, so.
Okay, so there were a couple of questions. Does Ariel want to take up and also answer, as you already did in the chat?
Yeah, sorry everyone. We just had some good questions. So one question was when we're talking about background conditions like D here, and we are setting them as external, on what grounds are we defining it as external? And I was saying that we have just decided to, at this circumstance, define it as external and ignore it for this purpose. But the point Yota was making is like we might initially consider the whole network as our potential system of interest, or then we might move to considering smaller parts of the network as our system of interest, and then we want to fix the background conditions of the rest of the network when we're just considering a smaller network. Why we might be considering only a smaller network will become much more apparent when we get to Angus's parts later in the talk, in terms of calculating integrated information for particular subsets of some large network. But Yota's just pointing out that we can do it. And then we had a different question about assuming that the system right now is modular and encapsulated. And that, again, is part of the assumptions of IIT, is that you've got a well-defined system, or network, sorry, made up of discrete elements that can hold discrete states that have some static transition probability matrix. So the transition probability matrix is stationary or ergodic over time in this circumstance. So we are assuming that it's modular and encapsulated. Obviously, that's an assumption that's not necessarily true in practice for real brains over time, but we can discuss that during the question and answer session at the end.
Yeah, just to add, you can consider it as a modular and encapsulated, but the more probably appropriate way to say that is, if we assume this system is composed of this small subset, then what we get as an integrated information structure is such and such. And then eventually we will test all the possible combination of the subsets. And then IIT's exclusion action dictates that what matters is the only maximum, and therefore the ones that after trying all subsets, the one that arrives as a maximum is the one that is corresponding to consciousness. And that's the kind of the flow of the logic. And there was also a question from Dawan. Is fixing or setting an intervention or just circumstantial, or does it matter? It's actually quite a good question. And in this tutorial artificial network situation, this is exactly intervention. And what Angus and Yota have already kind of alluded to as a sort of practical recording case, it is a circumstantial. Meaning that, you know, when the system entered in 0-1 state, then we treat it as, okay, so under this 0-1 state, what goes on to the next time step? Is there any other questions so far? Rob's question, I think we addressed, I guess. So let's move on further.
Okay. So from this full network TPM here, we focus on the case when these states of a current state, a current time step, and then focus only on A, B, C, a candidate system. So this is a minor point, but in the original IIT 3.0 paper, it says that we need to fix the states of background condition in both current states and the past states, but in the latest version, or maybe in Hi-Fi, they did not do it. What they do is just fix the state at the current time step. But we don't know why, but this is what the paper says. So
yeah, this is a very small kind of the example, but you know, you may find it into the future. There are some, you know, minor things that can be fixed in this way or that way, and ideally, as I said, action should dictate this or the other. But currently, there is some ambiguity like this, and we'll come back to this as a historical explanation by IIT at the end, if you have time. Okay, let's go.
Yeah, that was the last part of mine. So Ariel, can you continue?
Yeah, I'll take over now, and we can have a break for a couple of minutes after my section before we get into Angus's section. Just give me a minute to pull up.
So far, is there any other further question? You can now speak, or while Ariel is setting it up, or type in the question. So far, fine? Okay, let's move on then.
Okay, so Yota has explained the what we're interested in here. So we're interested in some network or some subset of a network with discrete states that can take discrete elements, and the whatever state the network is in at some particular time has some bearing on what state the network will have at the next time point. So the question we want to ask when we're going to be calculating integrated information later is, what impact is the network or particular subsets of the network or particular elements being in a particular state at a particular time point? What impact does that have on the future states of the network, or how does it constrain what the past states of the network was? So that's what we're going to get into now. So let's say we take some candidate system that's a subset of the entire network and some fixed background conditions. We can call a subset of that network a candidate system. When we are assessing integrated information for a candidate system, when a network is in a particular state, we want to perturb the system while keeping the external elements fixed. So we can fix the background conditions of D, and then having fixed what the background conditions of D are, we can look at the transition probability matrix for the candidate system. So this is what, hold on. Sorry, I'm behind on my slides. I thought I was repeating myself. Okay, sorry. So we're getting into the cause-effect repertoire. So what I was saying. So we've chosen some candidate system, and we are now looking at some candidate system or some subset of a candidate system, essentially all the elements that we haven't fixed as background conditions as part of that network. So we might want to know what the influence, can I turn on the video? Oh yeah, sorry. So we might want to know what the influence of any of our potential candidate mechanisms. So whether that mechanism is A, or whether it's B, or whether it's C, and this is whether it's A in an on state, or B in an off state, or C in an off state, or A in an on state and B in an off state, or the same for A and C, or B and C, or the entire system, A, B, and C. We want to know what the influence of that mechanism, so that subset of the system that we're interested in, being in a particular state has on the probability distribution of future states of the system. And so this is what we're defining as the causal properties of some mechanism. And we talk about the cause repertoire, which is like what constraints does that place on states that will occur in the future for the system, and the effect repertoire, which is given some mechanism in some particular state, what does that say about the previous states of a system that would have led to the system being in this current state now. So those are what we call the repertoires over the probability distributions of the states at either the previous time point or the next time point. So first, to try and make this clear, we're going to focus on the effect repertoire. Is everyone with me so far? Cool, I'm getting some thumbs up, so that's good. Okay, so in this circumstance, we want to know what the effect repertoire is of the candidate mechanism ABC. So we have our network ABCD, and we have our system ABC, because we've background conditioned out D. And then as a mechanism, we're taking ABC, where A is in an on state, B is in an off state, and C is in an off state. And having our mechanism in this particular state, we want to know how does that influence what the probability distribution of states will be in the next time step. So you can see here we've got ABC in the current state, ABC in the next state. And if A is on and B and C are off, we want to know what that does. So it's quite simple in this circumstance. What we do is we take the row of the transition probability matrix that corresponds to A being in an on state and B and C being in an off state, and we pull up the distribution of the probability distribution of next states. So here are all the theoretical possible next states, and this is the probability distribution over those states. And what you get on the left here is the effect repertoire of ABC when it's in the state A is on, B is off, C is off. And you can see here that all the mass is concentrated on this point where A is off, B is off, and C is on in the next state. So that's for considering the impact of this mechanism over the entire system at the next time point. But we can look at the effect of a mechanism over some subset of our candidate system at the next time point. And when we're doing that, we call that a purview. So a subset of elements of interest is what we call the purview of the mechanism. So for example, if we're keeping ABC as our mechanism, but we're only interested in B and C elements as our purview, we can see how is it that A, B, and C constrains the next state of not the entire system of A, B, and C, but just the purview elements B and C. So this is a graphical representation where the mechanism again is A in this on state, B and C are off, and we're looking at the impact of that on B and C in the next time point. So what we do in this circumstance is we marginalize over A at the next time step, because we are essentially just ignoring A at the next time step. Before I go on, is everyone okay with the term purview for the purview of the mechanism at some subsequent time step. This is for an effect repertoire, or if we were looking at a cause repertoire, we would be looking at the purview of a mechanism at a previous time step.
Okay, so just to if you struggling with this term, which is very difficult to remember, I guess, is that you can consider it as a sphere of the influence or target of the influence or something like that. Target of the cause, potential cause, or something like this. Okay, go ahead.
Yeah, so in this circumstance, the purview is only B and C, which just means we don't care about what's happening at A. So we marginalize over the states which only differ with respect to A, in the same way that Yota previously described. So we can do that, and we obtain our modified transition probability matrix. And now, once we've marginalized over A, what we do again to see what the effect of this mechanism ABC on the purview BC is we take the row that corresponds to our particular mechanism, and that gives us the effect repertoire for the mechanism ABC over the purview BC. Again, I will just keep going unless people stop me at this stage.
Go ahead.
Okay, so that was for a purview that was a subset of the entire system. We can also do the same thing where we take a mechanism that is a subset of the whole system. So in this circumstance, we have the mechanism being only C out of the system ABC, and the purview being only B and C out of the system ABC. And so the only thing that's going to be fixed now is the mechanism C in the off state. And what we want to know is, how does the mechanism C being in an off state at time point t constrain the purview B and C? So what does it do to the probability distribution of states over B and C at the next time step, ignoring the rest of the network? So again, what we do here is we take our transition probability matrix for ABC over the system, and we want to perturb it into all of its possible states with equal likelihood, see what the mechanism C's state is in, and then observe the effects that has on the purview B and C. But one thing to note in this circumstance is that the two purview elements B and C share a common input from A. So that means that when we're perturbing the system A, B, and C through all of the states that it can occupy, there's going to be some correlated effect from whatever the state of A is in at time step t onto whatever the states B and C are at time step t plus 1. In IIT, in its current formulation, we want to remove these correlated effects. And the way we do that is by introducing virtual elements. So the idea being here that instead of having a system here where C is our mechanism and B and C is our purview, and these are our other elements, what we do is to ensure that we ignore the impact of A having correlated effects on B and C, we introduce virtual elements where the inputs from A to B and the inputs from A to C are independent of each other. Sort of my way of thinking about this is that we want to know what the constraints of the mechanism C are at time point t on the purview B and C at the next time point. But if we don't introduce these virtual elements, then what will happen is when we examine B and C at the next time step and we perturb the system at the previous time step, we're going to learn about what A is as well, instead of just looking at the constraints of C. And so we are enforcing that a uniform distribution of inputs into B and C at the next time step comes from the previous time step by introducing these virtual elements. Although I'll talk about later how in the actual PyPhi calculations this ends up being not necessary. Is everyone with me happy here, or do people need to focus on that for a moment? Okay, I will continue that. So in this circumstance, then to remove the correlated effects of the inputs from A into B and C, we introduce these virtual elements where essentially we split A into input from A to B and input from A to C. And then given that, we do all of our calculations the same way we've been doing previously. So again, we're only interested in the effect that C has on B and C at the next time point. So we marginalize over A at the next time point. So we remove it as we've done previously. But we're also only interested in the impact of C. So we're going to marginalize over all of the inputs AB, AC, and B. So to skip through those. Now, sorry, were you saying something? I guess not. So we marginalize first over the input from A to B. Then we marginalize, and you can see in this circumstance, we have to normalize over the impact of the current state onto the next state, because we've ended up with a greater than 1 probability mass for the next state. So we normalize from 2 to 1, or from 1 to 1/2 down here, as you can see. Next, we marginalize over the input from A to C. We perform the same thing again. And now we're going to marginalize finally over B. So we end up with only C remaining, but now looking at the transition probability matrix that has C at the current time state onto B and C at the next time state. And we note that C is in the off state. So we're going to select C in the off state, and that gives us the effect repertoire for the mechanism C over the purview BC, with C being in an off state at the previous time point. So to recap briefly, we've got a system which is comprised of a set of elements with discrete states, with particular transition probability matrices resulting from that. And introducing virtual elements into this system is equivalent to finding the virtual transition probability matrix via perturbation. Ignoring elements from outside the purview or outside the mechanism is equivalent to marginalizing over those elements. And fixing the current state of the mechanism is equivalent to conditioning the transition probability matrix on that mechanism. We've got a question. Could you isolate the effective difference in outcomes between marginalizing versus making virtual elements and then marginalizing? I'm not entirely sure I understand the question. I think it might be answered in the slides that are immediately about to come up, but if I haven't understood that properly, we can pause on that again. Also now if you're, no, you're muted, so never mind.
Yeah, so, maybe that one, do you want to clarify your question?
No, he's right. It might be explained later. It's just a question. By isolate, I don't mean like experiment. I just mean in terms of explanation. So, I mean, given those two operations, if you take an element and you marginalize it out, okay, that has some sort of effect. And given an element, you in the cause situation, you first make virtual elements and then you marginalize it out. What is the ultimate difference in the outcomes that is implied by those two different types of operations?
Yeah, so we will be focusing on that in a couple of slides time from now. So we can go through that then.
Okay, and my short answer would be probably very different, but let's see.
Okay. Just before we get to picking up on Dawan's question, what we can also do is note here we're only looking at the effect of some mechanism on some purview, but we might want to know what the effect of this mechanism and purview is in terms of what that says about the unconstrained distribution over the non-purview elements. So taking this mechanism and this purview, what's happening in the rest of the system at the same time as well. And what we do here is we calculate the unconstrained distribution for the rest of the system at the next time point without conditioning on the mechanism at hand. So in this circumstance, what that means is we take A and we feed it we perturb the system at the previous time point. So we feed in a uniform distribution into A's inputs. And we note that at the next state, then A has some particular probability distribution over its future states, which in this circumstance is obvious because A is an OR gate. And then what we can do to look at what our particular effect repertoire, the effect of our effect repertoire over the entire system instead of just over the purview is we can take our purview and we can take the product of our purview with the unconstrained elements outside of the purview. So if you take BC here, for example, and you want to look at what BC and A do together, we just take this probability that BC is in an off state, which is a half, and we multiply it by either of the states that A can take in the next circumstance. So a half by a quarter gives us an eighth here, and a half by 3/4 gives us 3/8 here, where these states only differ by the state that A takes, whether A is off or A is on. And we can do this for every combination of the unconstrained A with our constrained purview elements here. And that gives us this probability distribution over the entire candidate system. So to get back to Darlan's question from before, in IIT, the way they define the system and the elements is that each of the elements has to be conditionally independent from each of the other elements at some time point. So they mean that the element state at time point t+1 only depends on the system state at the previous time point and not on what the state of any of the elements at a current time point is. So if you're thinking about this, it means that at a current time point, if some element is in some particular state, that's been determined only by what state the elements were in previously, not what any of the elements are in at this given time step. And this conditional independence of all of the elements at some time point from any of the other elements at the time point means that we can get the joint distribution of a number of elements, so some purview comprised of multiple elements, by just taking the product of the effect repertoire of individual elements. And this means that there's only one way to end up calculating the effect purviews, in that it's essentially finding the effect purviews for all of the individual elements. And then if you want the effect purview for a group of elements, you can take the product of all of those single element purviews. And there's no need to actually implement the virtual elements. So in PyPhi, there's no actual virtual elements used in the calculations. Does that answer your question, Dylan? Cool. Does anyone else have any questions before we go on to cause repertoires? I'm just gonna, how do I take a poll?
You need to set it up beforehand. So if you don't have it, that's fine.
Apologies.
Yeah.
I will just take people's silence as a understanding that we examined an effect repertoire, and we can do the same thing for a cause repertoire, which again is given some mechanism in some particular state. What does that say about the probability distribution of states that a purview, so a subset of elements of some system, were in at the previous time step before the time step that this mechanism is defined for. And we can essentially use the same calculations. So if our mechanism is in state off, then what we do this time is we switch around our TPM. So now our current state is defined in the columns and our previous time step is defined in the rows. Again, here is a graphical distribution where C is our mechanism here at time step T and BC is our purview here at the previous time step. And again, we want to first marginalize out the elements outside of the purview. So we marginalize out A, as we've done before. And we renormalize. Then we marginalize out the elements that aren't part of the mechanism. So first A, and then B. And then we condition on the current state of the mechanism being in the off state. And we obtain our cause repertoire from the purview BC in this previous state onto the mechanism C in the next state. So this is that cause repertoire, which you can see here. The numbers are wrong on the right here, but they're correct in the graph on the left. If we want to expand this to the full state space, as we did with the effect repertoire previously, we can multiply this distribution by the unconstrained cause repertoire of the non-purview elements. So we've seen how mechanism C being in the off state constrains what these purview elements B and C were, but if we want to look at then also in addition to what the distribution is over A, B, and C, where A wasn't constrained by the state of C, what we would do is we would recall that for a previous state, when it's being perturbed, any of the previous states are equally likely if we've perturbed our previous state into a uniform distribution. So the unconstrained cause repertoire of any of the elements that aren't constrained by C are simply going to be the uniform distribution. So A, even though it's normally an OR gate, in this circumstance, its previous states are just a half of being on or a half of being off. And then we take the product of that by our constrained B and C purview that's been constrained by C, and this gives us our cause repertoire over the whole system at the previous time step. So that's our expanded cause repertoire. So that's cause and effect repertoires. If you have any questions about cause and effect repertoires, you can ask now. Otherwise, we'll go into integrated mechanisms. So how do we actually use these cause and effect repertoires to calculate integrated information?
Is there any question? Otherwise, we'll go.
Okay, so we've got our system, we've got our network, we've got our system, we've got our cause and effect repertoires. What we would like to know at this stage is, given some particular mechanism and some particular purview, we want to know whether the effect repertoire or the cause repertoires are reducible to just the effects or causes of individual components of those mechanisms, or whether the mechanisms, causes, and effects aren't reducible to just the product of those elements together. So the idea here is, if we consider some mechanism A and C over the purview A, B, and C, where A is in an on state and C is in an off state, it has this following effect repertoire, which you can calculate if you want later. What we'd like to know is, what is the difference between this effect repertoire for the mechanism AC over the purview ABC, between that and if we partition the purview into just AB and C, and we consider the effect repertoire of this mechanism A and C over A and B, but also over C being unconstrained. So now C is no longer constrained by A and C. So we're comparing A and C over A, B, and C to A and C over just A, B, and C being unconstrained. So we can calculate, again, the unconstrained repertoire for C, and we can calculate the repertoire for AC over AB, and then we can take the product of those two to get the repertoire of AC over ABC, where C is unconstrained. And we can see that now that we have our unpartitioned original system and we have our partitioned system, which is where C was cut off from AC, that the effect repertoires in these circumstances aren't any different from each other. So in this circumstance, there's no information to be gained by including C in our purview. It makes no difference to the system whether C is included or not included in this purview.
There was some question from Paola about sort of the more psychological or philosophical kind of, aspect of relationship between causal repertoire and report. But I think that's probably better to be discussed at the end. Yeah, because it's not probably directly related to this part of the explanation. Okay, yeah, we'll come back to the report issue.
So this is selecting just one particular partition. So we've got some mechanism AC and some purview A, B, and C, and we're just partitioning C off from A and B. But in general, we're interested in all of the different ways that the repertoire can be partitioned or can be factored. And you can see here, this terminology is a bit confusing at first, but it's just saying there's some mechanism that's on top and there's some purview that's on the bottom. And we're taking the product of some mechanism over some purview by some unconstrained mechanism over some purview. We'll try and, at subsequent time points, make clear what we mean by this particular terminology. So what we want to do is, given some unconstrained or unpartitioned mechanism, we want to try and factor it into all the different ways that it can be possibly partitioned, and then compare those partitioned systems compared to the unpartitioned system. Sorry, I was just looking at Angus's response. And the way we're going to do that comparison between an unpartitioned and a partitioned effect repertoire, or an unpartitioned and a partitioned cause repertoire, is by using earth movers distance, which is what's used in IIT 3.0. But you could use any other sort of distance metric potentially if you were interested in doing so. So the way that earth movers distance is calculated is take some effect repertoire and some other effect repertoire, which is a probability distribution over states. We calculate the cost of transporting or transforming one probability distribution into another distribution, which is calculated by the sort of the distance you have to move in terms of Hamming distance, and by the mass that you have to move. So in this circumstance, you can see here you're moving 0.25 from each of these columns. So it's 0.25 by 1 plus 0.25 by 1 gives you 0.5 earth movers distance. What we are trying to do with all of these partitions, when we take our original mechanism and we look for all of the ways we can partition it, is to find which is the minimum information partition. So which is the partition that results in the smallest loss of information. And what that's going to do is the earth movers distance between the unpartitioned repertoire and the repertoire of whichever system has the minimum information partition is going to correspond to how irreducible the system is, or how much integrated information the system has. So and that is what Angus is going to go through for us.
There was some question from Dawan. He's asking whether the partitioning analysis, meaning the quantification by integration, is it similar or same as marginalization?
Is it the same as taking elements that are unconstrained and then marginalizing and then re-expanding? I think that is correct, yes. All right, I'm going to hand over to Angus at this point.
Really? Is this really correct? I'm not so sure.
Dawan, do you want to maybe just clarify the question before we go on?
Oh no, I mean, it really is just a question. It just seemed like the two sounded very similar in terms of how you first, the previous section you defined a purview and then you marginalized a bunch of stuff out, and then you are able to re-expand just by multiplying, right? And that operation sounded a lot like what was done just now within the purview to look at irreducibility. And so I guess my question is it really the same thing? And if it is the same thing, then I guess you could also do a similar sort of reducibility analysis at the purview level, right? Of whether it's good to apply this purview versus that purview.
So I think mathematically the operations you're doing are the same. So you kind of marginalize out elements which you don't want to look at. But the key with this integration part is within your mechanism purview, you want to marginalize in such a way that some part of the mechanism is no longer affecting some other part of the purview, if that makes sense.
Right, right, yeah. So I guess the intent is a little different, but I'm just wondering, is this type of analysis considered at the previous step? You know, before you even get to this level, do you ever use this type of analysis to decide what is a good purview, what is a bad purview?
No. So how we choose a purview, was that already covered? So actually, I'm about to go through that actually.
Yeah. Okay.
But yeah, so it's up until this point, there has been no integrated sort of analysis.
Okay, okay.
So
wait.
It's similar, and operations are actually also confusing and similar, but yeah, you might need to take some time to understand why we are doing this and why we are doing this, and how as a whole it makes sense to be consistent with the actions. It probably takes multiple time to think about it. Okay, go ahead.
So maybe if I can just summarize, so the cause effect repertoire is looking at the effects that the mechanism has on a purview. And the integrated part is when we split the mechanism, so that connections between, say, part one of the mechanism and part two and the mechanism and the purview, that part one and part two are completely independent. Does this generate the same sort of cause-effect repertoire? And if it generates the same repertoire, then we can basically say that the mechanism is not integrated and you have two separate parts. That's kind of the idea. So I go on to my part. So what Ariel was explaining just before was kind of looking at, say, one of these. So if we just look at the top left, ABC over A, what we're interested in with an integrated mechanism is how a mechanism affects a purview, and whether after we split some of these connections, A, B, C to A, whether the effect is still the same. So whether the probability distributions are the same. And what Dawan was just asking was, how do we determine what purview to select? And to do this, we kind of refer back to IIT's exclusion axiom, which is kind of, we want to determine for which purview the mechanism has the largest effect, and then we select that purview. So basically we repeat the integrated mechanism analysis for every possible purview. So for this mechanism ABC, you look at purview A and then B and then C and then AB and AC, BC and ABC, and at each of those we consider all the possible disconnections from the mechanism to the purview, and we kind of see how much the mechanism exists or is affecting the purview. So if, without going into the detailed maths for each separate purview, what you get is a different repertoire depending on the purview that you're looking at. And each of these repertoires, for each purview, you'll have an integrated information value. And the idea is we want to take the maximum, the purview which has the maximum value, and in this case it's ABC over AC, which gives 0.5, yeah. And this is referred to as the maximally irreducible effect repertoire. And what we do is we then repeat the same process once again into the past. So you select your effect repertoire, in this case AC, and you repeat the process to select your cause repertoire. And essentially, when you consider your mechanism, effect and cause and the associated repertoires and the associated integrated information values, this specifies a concept. And the overall degree of existence, you can think of it, so kind of how much the mechanism ABC here affects the system is the minimum of its cause and effect. In this case, cause and effect are both 0.5, so it will just be 0.5. The basic reasoning for taking the minimum of cause and effect is essentially, if we think back to the axioms, in order for the state of the system to be accessible to the system, it has to have both causes and effects. on itself. And so if one of these is zero, so in other words, the mechanism has an effect, but it doesn't specify a cause in the system, then you end up with a feed-forward system, and you don't have a system reading itself. Yeah, and now just typed in the chat that concept here is a specific term in IIT, different to the general kind of what we normally use in everyday English. Okay, and then what we do is we find the complete set of concepts for the system. So if we go back to the composition axiom, what we want to look at is kind of how much mechanism A exists to the system, how much mechanism B exists to the system, and then also how much mechanism AB, composed of A and B, contributes to or exists to the system above and beyond AB. So what we do is then we repeat for every possible mechanism, so A, B, C, AB, BC, and ABC. And for all of these, we repeat the integrated information analysis where we find the purview, which generates the highest effect information and the highest cause information. And the idea is that this set of concepts specifies this cause-effect structure, which is supposed to correspond to the conscious experience of the system. So this structure is all the information which is accessible and readable by the system itself.
Wait. Just to make a note, if you are very alert right now, you might notice that there is missing component here among the power set of all the combinations, which is AC.
Yeah.
And it turns out that if you do exactly the same analysis on this AC component, you will find that the small phi value to be 0. And that's the reason why we don't have it here.
Yeah, and then at a higher level, what that means is mechanism AC doesn't specify any information which is readable by the system itself. So if there are no questions at this point, then next, so this structure is basically what the conscious experience of a system is. And one problem which some of you might be able to see is kind of what if you have a case where, say, mechanism A only affects itself, A. So if it's A over A and A over A here, and what if mechanism B only affects itself, so B over B and B over B? In that case, you might have a system which isn't actually whole and integrated. So even though A exists to A and B exists to B, A and B might not exist to the whole system ABC. So what we do next is we want to try and find the whole system. So this where the entire structure is existing for the system. So you can kind of see here, this is illustrating what I said before. So if you have a system which looks like this, where W is connected to X and Y is connected to Z, you can build your conceptual structure, your cause-effect structure, and you'll find that mechanisms W and X are just going to affect or have a purview within W and X, and Y and Z are only going to affect things within Y and Z. And you can kind of see if you split this system into W, X, and Y and Z separately, you're not going to have any effect on the cause-effect structure. So the idea of this is if you are looking at a candidate system W, X, Y, Z, this candidate system actually reduces into two separate systems, W, X, and Y, and Z. And what we want to do now is try and find how much, or kind of, if we separate the system into two parts, do we get the same cause-effect structure or not? So if you consider a candidate system A, B, C with whatever connections between them, what we want to do is we want to separate the system into two parts. And we can do this just by separating it into one sender and receiver. So if we go back to the first axiom of information, in information you have a sender and receiver, and this can't be one whole integrated system because your receiver, what's reading, your receiver is going to be separate from your sender. So it's not reading itself. And so the stuff which is the sender is sending is not kind of accessible to itself. So the idea is to have a unidirectional cut, which separates the system in such a way that you have connections from one set of the system. So for example here, BC can go to A. You can't have vice versa, A to BC. And then this is just slight details. So once you make this cut, you just rebuild the TPM. So here we've noised the connection from A to B and A to C. So if we just looking at the TPM for A, which has inputs from B and C, you just build as Yota already went through. So if you have a particular state 0, 0, 0, you'll get this set of possible states with these probabilities, and then 1, 0, and then 0, 1, and then 1, 1, and you get this TPM for A after making the cut. And then you repeat for B. And note that because if we go back here, we don't have any connections from A to B, then what we do is we essentially just marginalize A out of B's TPM to get this. And then we repeat for C, which gives this. And then once again, you expand to the whole set of states A, B, and C for each part of the system. So here you have the TPM for A, TPM for B, and TPM for C, given every possible state of the system after we've made this unidirectional cut. And to recombine the system into one, we just do a tensor product between all the TPMs. So this would be like this cell times this cell times this cell would give this, and then this times this times this would give this one, and so on and so forth. And so if we compare, say, the full TPM, so this is without any cuts, and this is with the system level cut, you can kind of see there's already some sort of difference. And the thing that we want to do is we want to compare the difference that this cut makes. And if this cut makes no difference between these two TPMs, or more specifically these the cause-effect structures specified by these TPMs, then we can say that the system decomposes into two separate systems. This is what I said. So what we want to do is we just want to quantify how different the cause-effect structure is between the full system and this disconnected system. So on this slide here, we have the cause-effect structure for the whole system, which was on the previous slide. So here we have A, B, C, A, B, B, C, and A, B, C, and how the degree to which they exist to the system, and also the specific information which they give to the system. And without doing all the complicated maths, if you were to build this using the new TPM after making this disconnection from A to BC, you'd get a cause-effect structure where only B has non-zero integrated information. So A, C, and everything else, they have zero integrated information, so they don't exist to the system after making this cut. So what we want to do is we want to quantify the difference between this system on the top and this system on the bottom. And as before, when we compared probability distributions at the mechanism level, we can do this using Earth mover's distance. And the idea is essentially to find how far away the distribution specified in the full system are from the distribution specified in the split system. So for example, we would be comparing for mechanism B, we want to see how much it takes or how far it is to move this distribution, B over AC here, to B over C here, and also how far it is to move B over A here to B over A here. So this is kind of illustrating exactly the process. So it's just kind of exactly this is just Earth mover's distance between this distribution and this distribution here, which is these two in blue. And this one is just the earth mover's distance between these two in green. So from here to here, after making the cut. And it gives this distance. And what we're concerned with is, what we're moving is kind of the degree to which this mechanism exists. So what we want to do is we want to weight this distance here, 0.17, by the degree to which they already exist in the system, which is 0.17 again. So this is the conceptual distance. So this is the earth mover's distance between the probability distributions. And then we weight it by the degree to which the concept already exists in the system. And that gives a distance of this. So this is the cost of moving from this concept to this concept after making the system level disconnection. But what happens to all these other concepts, A, C, AB, BC, and ABC? So they don't exist after making the system level cut. So what we do is we compare them to the case where, to essentially the case where the probability distributions give no information to the system. So I think there's an illustration here. Yeah, so these distributions here, if you use these distributions, you'll always get an integrated information value of 0. So what we want to do is we want to move these concepts towards this null distribution here. And once again, you find the earth mover's distance between this distribution here in blue and this one here and one's in green. You just sum those together and weight by the degree to which the concept originally existed, which is 0.17. So this would be 0.583, which is the conceptual distance between these distributions here and here, weighted by the degree to which the concept exists, which is 0.17, and the same for each of these. So this would be a conceptual distance multiplied by the integrated information of the concept. And then essentially what you do is just sum everything up to give the total distance between the full conceptual structure, the cause-effect structure of the full system, and the cause-effect structure of the disconnected system. And this will give you this distance here. And this is what we refer to as big phi. So this is the measure that you'll generally see in papers talking about integrated information, this integrated conceptual information, which is the distance between the full cause-effect structure and the disconnected cause-effect structure.
Yeah, was a comment from that one, and I actually wanted to make a comment about this. So can you go 1 or 2 slides back? Yeah, I think so. That one is asking a question about this. Where does this green bars come from when there's nothing is assumed? Angus, do you want to explain?
So these would be essentially the maximum entropy distributions. So
the
essentially,
blue one, that's the past. Yes.
Yeah. So the difference between the maximum entropy distributions between the past and the future is kind of, if you, I might get this wrong, but in one direction, I think it's the past. So if you have your mechanism, if you have the state of the mechanism at time t, and you don't know anything about connections or whatever in the system, so you're really taking the perspective of the mechanism, then kind of, if you look towards the past, you have no idea what states the past could have been in. So that's why you take the maximum entropy distribution into the past. But for the future, what you can do is you sort of know your own so you know the connections within the mechanism itself, because you are the mechanism. And so what you can do is you can kind of think, okay, if I was to take the maximum entropy distribution, so if I was to take any state, what would this give me in the future? And that's how you get the maximum entropy effect repertoire, which is kind of, if I perturb the mechanism into every state that the mechanism can take with equal probability, what is the resultant effect distribution? And that's how you get the null distribution for the future, the green one.
Yeah. So kind of like mean of all states. That's more or less, yeah, correct. That this basically, the unequal distribution comes mainly from the fact that the mechanism that, let's say, or and or XOR kind of mechanism for each of the A, B, C to become on is different. And that's reflected in this future distribution or effect distribution. Okay. Yeah.
Okay. So yeah, we got up to here. So you have this integrated information, which is kind of describing how much you can consider your candidate system as one system as opposed to two separate systems. But as for the mechanisms, you can disconnect your system in many different ways. So you can disconnect inputs from A to BC, but you can also disconnect inputs from B to AC, and basically all these. So every possible disconnection you can think of which separates your candidate system into basically a feed-forward system between one part and another part. And you repeat this whole process of building the disconnected cause-effect structure and finding the distance between the original full cause-effect structure and these disconnected ones. And as similar to the mechanism level, you take the cut which gives the minimum big phi. And once again, this is the reason we take the minimum is because if there's any one cut which gives 0 big phi, then essentially it doesn't matter what other cuts you do, your system is essentially two separate systems, or one feeding into the other. And we refer to this, the partition that we choose as the minimum information partition. It's basically the same idea at the mechanism level. Yep, so this is just saying we take the minimum big phi value as the big phi of this candidate system. And just to recap, you interpret this as kind of how much making a cut to your system would make to the system, essentially. So if it's 0, then you have two separate systems. Are there any questions at this point?
Are you going to talk about your slide, the data slide?
I can do it at this point. I was going to do it at the end, but this would be a good point to do it as well. So
yeah.
But just to summarize here, basically everything up to here is what PyPhi does, and what follows is kind of something that we have to do manually outside of PyPhi. But I have a figure here which basically summarizes all the steps, all the computations which are being done in PyPhi. So if I make this full screen.
Okay, there was a question from Shim, but maybe it's better to address it after we show Angus's slide, I guess. So just hold on one slide.
Probably maybe this is the better one. So from A you have your system, and then B you have your measurements, and then you just operationalize the states of your measurements into discrete states. And from these states you build a transition probability matrix. And from here you can assess all your cause and effect repertoires just by performing operations on this matrix. And what you want to do is you want to essentially look at every, say for a mechanism, you want to look at every possible purview. So the mechanism here is red and the purview is in white. And you want to see the information that your mechanism gives about your purview, which is basically this distribution here, obtained from the TPM. And what you're interested in is how much this information is irreducible. So what you do here in E is you make some sort of cut. So here you disconnect, say, A from A, or A from B, or A from A and from B, and you compare the resultant distributions with the original distribution that you had. And you repeat this for all possible purviews. So this is for purview AB, and then you repeat for purview A and repeat for purview B. And out of all the purviews, A, B, A, and B, you want to take the purview which gives the maximum integrated information as your core effect or core cause. And then if we go here to G, what you do is you basically so you have your cause and effect for your mechanism A. for whatever purview, which in this case happens to be A and A in the past as well. And you repeat for all the possible mechanisms. So you have A here, you have B here, and you have AB, and they all have their integrated information values. And they all have their cause and effect repertoires. And what I've, in the color here, you have yellow, you have the cause effect repertoire. In blue, you have your concept. And in green, you have your cause effect structure. And this is for your full system. So if you assume everything's connected. And what you do is, if you go to H, you impose some sort of system level disconnection. So here we're reducing the system into a feed forward system from A to B. And you essentially redo the entire process. And you get your cause effect structure for the disconnected system. And you do this for all possible disconnections, but here I've shown only for one. And you want to find the distances between all these distributions here, the cause effect repertoires, weighted by the degree of existence that each concept has, and sum them up together. And in the case where, so here if you look at this column here, you have different amount of existence or integrated information for mechanism AB when you consider your whole system and you're disconnected. So when it's whole, you have 0.0065, and when you've imposed your system level cut, it's 0.0038. And what you do is you kind of weight the distance between these distributions by the common amount of existence. So it'll just be 0.0038 times the distance between these distributions. And what you have left over, that's this here. And what you have left over, which is 0.0065 minus 0.0038, you move this to the null distribution that we were talking about before. And basically, this whole weighted summation gives you this big phi system level integrated information, essentially.
Okay, great, Angus. So now to take Shin's question, you can jump in. So his basic question is that, how much of all of this, like marginalization and also integrated information analysis, are they really realistic manipulations in biology, including lesion or muscimol or freezing and so on, probably also optogenetics. And he's basically concerned that how much of this is number playing and how much is real sort of biologically relevant operations. And the reason why I wanted to show this one first is that we can, at least from the observation, we can compute these things, and we can map onto these potentially with the real connectivity. In the first part of that talk, we also mentioned that usually we do not have the connectivity matrix and also mechanism of the neurons directly, right? But we can compute everything on the actual, the case where we know the mechanism and the connectivity. So our example here, in a sense, kind of as a sort of serving as a test bed for the future, where if the result of this type of analysis is completely different from the actual, connectivity-based analysis, then you can conclude that, oh, okay, so this is just a number playing. But so far as we are understanding the theory and also putting into the practice, such as the your data, if we use 2 channels from one brain and another 2 channels from another brain, we can find reasonable conclusion about integrated information analysis because they are not physically connected and so on. So I think it is a matter of the empirical investigation. That's my answer to some extent.
Can I jump in?
Yep.
So I knew what now the answer, and I'm to some extent satisfied. But are you suggesting that if you are a believer of integration information theory, then future neuroscience has to come up with techniques of shutting off or cutting or eliminating particular element in a more perfect way, more purified towards the mathematical model. And without that kind of neuroscience, you would never understand consciousness. Is that what you guys are saying?
In a sense, yes. And that's why I think, this theory is interesting. It requires invention of a new technique and a new sort of the requirement of experimental paradigm. And in a sense, currently, many people are doing TMS-EEG experiment right now, right? Mm-hmm. But that's, I would say it's probably fair to say that around 2000 or so, when Masmini and Tononi started that experiment, it came from partly this inspiration of this theory, where to know actual mechanism of the brain, we need to perturb the system and then record the response.
And except that there are natural perturbance like anesthesia and pathology and stuff like that. But it seems like your math requires much more exhaustive, systematic, every possible combinations of perturbance is necessary. Exactly. That sounds unrealistic to me.
Yeah, unrealistic if you think about only one thing, but if you think about Allen Institute, where they have a resource to do, equate brain connectivity and so on, and then try to perturb one cell at a time after identification, it may not be theoretically implausible, right? At least.
Okay, we can talk about. I'll stop here.
Okay. And Mohammed asked question: how much the way we decide the method of the binarization would affect the big phi? Angus, do you have a slide for that discussion?
No, but I think Ariel basically gave the response, and essentially, when you discretize your recordings in different ways, you're basically imposing different sorts of assumptions, and really, we just don't know the best way of doing it, and we are just doing it empirically and trying different ways of doing it. So far, we haven't seen any kind of big effect of using different methods. What we see is kind of big phi will go bigger or smaller, but whatever experimental manipulation you've done, the effect will still be there. That's what we've seen so far.
Yeah.
Okay.
So Paula is also making comment.
I think we should probably leave Paula's question, because it's an excellent question, but for the end after Angus just does his last bit on complexes.
Yeah, that's good. Is it okay, Paula? Yeah.
All right. So complexes, at this point, there's not really any more calculation being done. What this section is essentially doing is addressing the questions of how do you determine what your system is, or what is outside the system, what is inside the system, what is the scale of your system, and those sorts of questions. So we did our analysis on the system A, B, C, but because exclusion axiom, what we need to do is we need to find the system which gives the maximum big phi, essentially. And that is a system which is relevant to consider for consciousness. So what you do is essentially do the whole process again. So before we did for ABC, so now we look at AB, BC, AC, and for all these, so at this point, AC would be your candidate system, and you'd construct the cause-effect, you make the cause-effect structure for this system, impose a system-level disconnection for this system, and then compare those, compare the cause-effect structure, the cause-effect structures between the force system and the disconnected system for this AC here, and you do it for every possible candidate subset. So here we've got grouping AB, AC, BC, ABC, and then ABCD as well. And some grouping of these elements is going to give you a maximum big phi value. So if you look at the connections here from D to ABC, because it's only a feed-forward connection, so D is affecting A, B, C, but A, B, C is not affecting D. So this system A, B, C, D reduces to two systems by doing this system-level disconnection here. And if we look at, say, only AC or AB, this doesn't capture all the information which is available to the system. So in this case, ABC is giving the maximum big phi value, and this would be the system which you would say is conscious. And by doing this, you can see how you can determine where your system starts and where it ends. And everything inside the system that you determine is part of the system and is affecting itself and is able to access its own state, in a sense. And this is the last slide. So what it means by, so it says you have to conduct this search for big phi across all spatiotemporal groupings. What this means is, I think someone asked about the time scale. So what is a time step in the brain? This is something that you also have to search for. So your T and T+1, you might have to consider higher sampling rates or lower sampling rates. And you just need to, and essentially you have to repeat the process until you find the big phi which gives you a maximum. So that's the temporal aspect. The spatial aspect is kind of what do you consider as logical units? So someone asked kind of, do you have to consider every single neuron in the brain, for example? And it might not be the case that that the scale of neurons is relevant. It could be that, say, cortical columns are the scale which is relevant for consciousness. And what you might do in an experiment is you might combine, say, nodes A and B and just average your recordings across this to form a larger scale grouping. And once again, at these groupings, you repeat the analysis. You build the cause effect structures and you find where big phi is maximal. And once you find across all spatial temporal groupings and across all boundaries, the boundary and spatial temporal grouping which gives you the maximum big phi is the one which is generating consciousness. And that's the end of these slides. So, yeah.
Okay, thank you. And let's start taking Paula's question. I already partially answered second question from Paula about what's the sort of the necessary kind of the perturbation or cut. And I said that, for example, one of the inspiration from IIT is we do need a unidirectional cut, and that would correspond to not the lesion or TMS, but rather it's more to do with optogenetics type, manipulation, where you can actually cut the connection or stop the connection from prefrontal to visual cortex, but not the other way, or something like that. And then maybe also to discuss about your previous question about the report and IIT. Angus, do you want to answer first, or?
Yes. So the idea is the conceptual structure is reflecting the exact experience that the system is having. So the conceptual structure is, the cause effect structure is telling us all the information which the system itself can access. And because this is what the system is experiencing, this presumably would be what your subject would report. So there should be a correspondence between this cause effect structure and what your subjects are reporting they are experiencing.
Right.
And in fact, sorry.
Go ahead.
I was just going to say that's one of the ways you can potentially falsify IIT, which is if you have subjects reporting the same experience but with wildly different information structures derived from IIT, or vice versa, then that's evidence against the theory.
Right. And also in general, I also want to point out that because of this unidirectional cut requirement to find this big phi, which maximize this, a number, most likely any kind of feed-forward architecture, such as retina to LGM or motor cortex to muscle, these kind of things will be outside of this so-called complex. Okay? And also same thing probably is likely to be true for many of the architecture such as the cerebellum, which is receiving again, kind of unidirectional input from basal ganglia to cerebellum and then to the cortex and so on. Loopy structure with a parallel, with minimum interaction between them. These are the kind of structure that minimize the big phi value when it's included. And then there was a question from Aniko. You could try to set up a similar system of integrated networks based on the reports only. I don't understand what you mean. By the way, I have to leave, unfortunately, so I might leave, but you can go on for the discussion.
Okay. We said we would not record the questions and answers. Should we?
Oh, okay. Maybe then let's stop here, the recording. Yota?
Okay.